Let's get started then. I hope you are all doing well. Welcome back to the class. Let me know if you have trouble viewing the video or my voice cutting off. Okay, and also you should be able to unmute yourself and speak up as needed during the class, just as a regular class session. Okay, I would prefer that rather than sending in the chat messages, because I might be missing them as I'm teaching. Okay, so let's get started. Before I get started, any questions, concerns related to the class? By the way, I'm recording this, so this will be available online as well. I will be providing a link for this later on once uploaded. So this should also be available. Okay, if nothing, then let's get started. So just a quick recap of what we have done in the last class. Again, these are some of the very important concepts, very useful for the final exam, but also at the same time, these are also very useful in terms of trying to build more complex systems. And we will see, hopefully we will see in this class, we'll conclude most of the discussion on the sequential building blocks, and then we'll try to put them together to build useful systems. Okay. So in the last class we talked about the D flip-flops, the different kinds we can have. We started off with the level triggered flip-flop. Again, we talked about what triggering means. When we say that a flip-flop is triggered, that means the output responds to the input. That's when we say that the flip-flop is triggered. The flip-flop is applied a clock, and when we talk about a level triggered flip-flop, for example, a high level triggered flip-flop, only when the clock signals are high, my output sees the input. Or in other words, my output can respond to the input. As long as the clock signal is low, my output does not even see the input, so there is no changes happening. Even if there are changes on the input, there will be no changes happening on the output of the flip-flop. Okay. And we also spoke about the master-slave configuration of the flip-flop, where we took two level triggered flip-flops, and then we configured them as a master-slave flip-flop, where one flip-flop drives the other one. So the flip-flop that is driving the other flip-flop is called the master. The one that is being driven is called the slave flip-flop. Okay, and the clock that was applied to the master was the actual master clock, and then we apply the inverted. So basically, we run the clock through an inverter and apply that to the slave clock. And in effect, when we did the timing diagram for this flip-flop, we concluded that corresponds to the whole configuration corresponds to what is called a negative edge triggered flip-flop, right? So where my outputs are triggered on the edges rather than the levels this time, because the edges are very short in terms of the time it takes for the edge to happen. So you can ensure that within a clock cycle you can only have one change in the output. Even if you have some spurious inputs, those inputs are filtered out automatically by the edge triggered flip-flop. Okay. So in effect, we looked at the D flip-flop, the edge triggered flip-flop, where let's say that's your D flip-flop. This is how we specify the edge. That's a negative edge triggered flip-flop. That's Q and Q prime. This is where you apply the clock. So in other words, this particular flip-flop gets triggered every time a clock signal goes from high to low. That's your negative edges, right? These are your negative edges, and every time my flip-flop goes from high to low, my output responds to the input, right? So that's your flip-flops. And then we also looked at the characteristic table for this. Now for edge triggered flip-flops, we talk in terms of, okay, so you have your D input, you have your Q T plus 1, okay, What this means is I am applying an input on D, on my D input, when the on the inactive edge of the flip-flop. Inactive as in when the flip-flop is not triggered. Right? I am applying an input and I am waiting for the active edge to happen. In this case, the active edge is the negative edge, and I want to see what happens, how the flip-flop is responding, the output responds when that active edge happens. In this case, because it's a D flip-flop, my output simply follows the input. The output, once it's triggered, the output goes to 0. Again, when I apply a D equals to 1 on the inactive edge of the flip-flop, once the flip-flop gets triggered, the output goes to 1. Okay? So that's your edge triggered flip-flops. Towards the end of last class, we also discussed, again, we configured using a D flip-flop, right? So you had a D flip-flop, Q and Q prime. Again, that's a negative edge triggered flip-flop where you apply the clock. But we modified this flip-flop to have some additional combinational blocks here, something like this, right? So you have two AND gates, and one of the input to the AND gate is J. We call it J. The other input is a feedback going to Q prime. Okay? And then here you have one of the input of this AND gate is K. The other input is Q. And we wanted to analyze this circuit. This is, and of course, we need to complete this. So the outputs of these two go into this OR gate, and the output of the OR gate goes into the D. Okay? And we know that the output here, the intermediate output here is J Q prime. The intermediate output here is K prime Q. Right? And both of these are being added up, as in or ORed together with the OR gate before they are passed on to the D. So in other words, my D input D is simply J Q prime plus, it's again this is J Q prime plus K prime Q. And we wanted to derive the characteristic table of this flip-flop, which we did. So I'm going to quickly go over that characteristic table. So what we found was, again, so you have two inputs for this particular configuration, and we call this the JK flip-flop. Okay, so I have two inputs for that flip-flop. I can just box this up. Right? Inside the JK flip-flop is what you have here. And then, of course, I can take the output. This is my output. And that's the clock input. This is where you apply the clock for that block. So this is what we had before. Okay? And so I have two inputs, J and K. So let's derive the characteristic table for this. I know exactly how this particular block works, which I have the characteristic table for that block already. So now I can again apply the modular design process. Right? So I have J and K. These are my inputs to that flip-flop. These are the independent inputs. I can apply any values on J and K. And then I have the intermediate output in this case, which is actually connected to D. So I will call that D. Right? And then I have Q and Q prime. So because this is an edge triggered flip-flop, I can write in terms of QT plus 1, as in I'm applying a J and K inputs on the inactive edge of the flip-flop, and I'm examining what's going to happen to the flip-flop once the flip-flop is triggered. In this case, the D flip-flop is triggered. Okay? So let's look at all possible combinations for J and K. I have 0, 0, 0, 1, 1, 0, 1, 1, and for each combination, let's see what your D input is, right? Because the output of this combinational block here, the output of this combinational block, in this case, is nothing but D, right? The output of that combinational block is nothing but D. Okay? Now, with J and K of 0 and 0, J and K of 0 and 0, what do we have for D? You just plug in the values. With J is 0, that means that's 0 times Q prime, that goes to 0. K is 0, K prime is 1, and then that leaves me behind with QT, right? That's QT. Okay? That's the instantaneous value of, that's the value that's the present value on D, and once this particular flip flop is triggered, right, again the output follows the input for a D flip flop. So once the flip flop is triggered, the output remains as Q of T. The output doesn't change, right? And when the output doesn't change, that means we consider that, we associate that with the memory condition. So when you don't want to change the output for that particular configuration, we'll just place J and K to be zeros, in which case my output just gets recirculated back to the input. With every clock pulse, that same output gets recirculated back to the input, and with every triggering instance, that same output, same input goes to the output, right? So basically that's your memory state, memory condition. Now what about 0, 1? You apply 0, 1 on this. So again, J is 0, that means that 0 times Q prime, that goes to 0. K is 1, that means K prime is 0, right? So that goes to 0 as well. In other words, my D input that I'm applying here is basically 0. I'm applying a 0 on my D input, and once the flip flop is triggered, right, once this D flip flop is triggered, the output follows the input. So my QT plus 1, once the flip flop is triggered, is basically 0. Right? So in other words, and that corresponds to the reset condition, reset, where when you want to write a value of 0 on my memory, for example, I will put a 0, 1 on my J and K values respectively, and I get the reset condition. 1, 0, my J is 1, that means that's Q prime, right? That's Q prime. My K is 0, that means K prime is 1, right? K prime is 1 plus Q. And we know that Q plus Q prime, or X plus X prime, from Boolean identities, we know that that's always equal to 1, right? So that's 1. So now I'm applying a 1 on my D input. Once the flip flop is triggered, my output follows the input. The same thing is obtained. So basically, in other words, this is called the set condition, where if I want to write a value of 1 on my output, I'll place a value of 0, I'll place a value of 1, 0 on my JK inputs. Okay. All right. And then finally 1, 1. Let's see what happens when I place a value of 1, 1 on my J and K inputs. What do you think will happen? So J is 1, so that remains, so that's Q prime here, right? J is 1, 1 times Q prime is Q prime, plus K is 1, I substitute here, K prime is 0, that goes to 0. In other words, when I have J and K values of 1, 1, I'm placing on my D Q prime of T. So whatever value was there, I'm inverting that value, applying on D, and I'm waiting for the next triggering instance. So once the flip flop is triggered, output follows the input, so my output essentially remains as Q prime of T. Now what does this mean? This is something that we have not seen before, right? We have seen all of these when in the discussion of the SR flip flops. We have seen all of that except this. In the SR flip flops, we got this as the forbidden condition because the output was indeterminate. But in this case, we are actually getting something useful, which is it's a determinate state, as you can see. When I apply 1, 1, I am basically inverting on the output whatever value was there in the previous instance, previous triggering instance, right? So, and this particular state is called the toggle state or toggle condition. So when I'm applying a 1, 1 on my J and K inputs, I'm essentially toggling the output from 1 to 0 or 0 to 1, depending on what was there before. Okay? All right. Now to illustrate this better, what we should do is we can actually take the aid of timing diagram. Okay. Now we are we know, we have seen this before, we don't have to worry about all of these conditions 0, 0, 0, 1, 1, 0 for J and K inputs. The only condition that is new is 1, 1, right. So let's actually examine this. So, but before that, now that we know exactly how this flip flop actually functions, we don't have to worry about this intermediate intermediate inputs or outputs, right? And those are the inputs to the flip-flop for the JK flip-flop. Those are the outputs for the JK flip-flop, and that's the characteristic table for a JK flip-flop. Okay. All right. Now let's draw the timing diagram for this one. So now that we know all of that, so let's actually take this out. And now for a JK flip-flop, we can put everything inside a box. We don't need to know what's inside the box. We already know what's inside the box. How do we construct a JK flip-flop? So now we can basically talk in terms of, you have a J input, K input. That's your enable input. That's a negative edge triggered flip-flop, Q prime. Right? I have two inputs to this flip-flop, two outputs Q and Q prime, and then the enable input, where you apply the clock for that flip-flop. Okay. All right. So now what I'm trying to do now is I would like to see what happens when I apply on my J and K values, K inputs. I apply a value of 1, which corresponds to this particular situation, right? When I'm applying a value of 1 constantly on my J and K inputs, what's going to happen to the output? I'm monitoring Q as a function of time, and I'll use the timing diagram for this. So I have, again, when I draw the timing diagram, I'll always draw it with reference to the clock. This is my clock, ones and zeros. Once I draw the clock, I will identify what are my active edges here, because that's an edge triggered flip-flop. So I would first identify the active edges. In this case, this is a negative edge triggered flip-flop, as you can see, because with that bubble. So these are my active edges. And I have these active edges happening exactly once per clock cycle, right? My active edges happen exactly once per clock cycle. Okay. I don't have to worry about J and K displaying on the graph because they are constant at 1. So it doesn't make sense to actually have them displayed in this particular timing diagram. Okay? So that's my clock. And I'm monitoring Q as a function of time. Again, I assume that, and these are my active edges. I assume that Q was 0 to start with. At time t equal to 0, I assume my Q to be 0. All right. Now, when my Q is 0, once it's triggered, this is my first triggering instance. My Q is 0, nothing happens until the first triggering instance, because that's memory state, right? Once my flip-flop is triggered, what's going to happen to the output? What do you think will happen to the output based on the characteristic table that is provided here? You can see that when my inputs are fixed at 1 and 1, every time my flip-flop gets triggered, the output toggles. So in this case, this is Q of t, right? That's Q of t. That's Q of t plus 1 becomes Q prime of t. So the output toggles, and it remains in this state until the next triggering instance, which is that. On the next triggering instance, again that output toggles, output becomes low. Next triggering remains low until the next triggering instance, which is this, toggles, because that's my flip-flop gets triggered, and so on. So this is a useful state. This is called a toggle condition or toggle state for this particular flip-flop. Okay. Now what can you say about the frequency of my Q of t? Frequency of Qt compared to clock frequency, let's say FC. That's my clock signal, which has a clock frequency of FC, let's say. That's my Q of t. My output toggles at every new triggering instance, right? 0 to 1, 1 to 0, 0 to 1, 1 to 0, and so on and so forth, right? Yeah, and you can directly observe from this diagram that my Q of t in this particular situation, my Q, the frequency of Q of output of Q is essentially FC over 2, right? You can also think of this as a frequency divider. It's basically dividing the clock frequency by half. Again, you cannot have in any system that you're designing, you cannot have any component that is running at a frequency larger than the clock, right? It has to be your clock will be your master clock is the one that determines the speed, and everything else runs at that speed or less than that speed. Okay, so in this case, the frequency of this particular output, once J and K are both tied at 1, is FC over 2. Okay. Now let's consider this scenario where I use not just one but let's say 4 of these JK flip-flops, okay, and arrange them in this particular configuration. So I have 4 of these flip-flops, identical JK flip-flops, okay. Okay, I have 4 flip-flops. Let me call this JD, KD, call this QD, JC, KC, QC, JB, KB, QB, JA, KA, QA. Although I do have Q primes for each case, I'm just not displaying them. Okay, and let's say these are all negative edge triggered flip-flops. So I'm applying the master clock here. Okay, and I'm tying each of these flip-flops to the toggle state, as in I'm tying all of them to 1, a value of 1. That means each of my flip-flop are configured to be in the toggle state. Right? So each of my flip-flop are configured to be in the toggle state. Okay. All right. And then for the rest of the flip-flop, the way I apply the clock, the signal from the first flip-flop goes, the output of the first flip-flop goes as the input, clock input to the second flip-flop. The output of the second flip-flop goes as the clock input to the third flip-flop. The output of the third flip-flop goes as the clock input to the fourth flip-flop. And I'm monitoring what my QD values are at each time. All my Qs. This is my QA, QB, QC, and QD. Okay? All right. Now, let's draw the timing diagram to understand this. So let's draw this here. Okay. All right, I'll start with the master clock. That's the first you need to reference to for anything. That's my master clock. and I'm now will be drawing each of the output as a function of time, starting with QD. Again, I'll identify my active edges. In this case, these are my active edges. Those are all my active edges. So I will make sure that I drop these active edges down. So because all the action happens at the active edges, so you might as well have this reference. And then we will draw each of these outputs, QA through QD, how this changes. You may already guess what's happening. With QD, at every active edge, the output toggles. Every active edge of the clock, the output toggles, right? So that's assuming QD to be 0 in the beginning. It toggles, switches back, toggles, toggles at every active edge. And the frequency of the signal that I get from the QD is basically half the frequency of the master clock. That's what I get for the QD. Now QD is what is being supplied as a clock to QC flip-flop, JC and KC flip-flop, right? So because this functions as the clock, I will identify these active edges, because these are the active edges at which my QC values toggle. Okay, so when I draw QC, assuming that QC is 0 to start with, I start with the 0 value. It toggles on the first active edge, which happens here. Toggles on the next active edge, which happens here. Toggles on the next active edge, and so on. That's my QC. Now, with respect to the master clock, my QD was FC over 2. If this is FC, the frequency of the clock, my QD was FC over 2. My QC would be FC over 4, right? Compared to the master clock, that's divided by 4. Likewise, if I wanted to do QB, for QB, my QC is the clock. So these are the active edges. Again, this is a negative edge triggered flip-flop. These are the active edges for QB, and likewise you can draw for QB as well. So then my QB gets triggered, gets toggled on this the first active edge, toggles, toggles, and so on. And you can see that the frequency of QB would be FC over 8 compared to the master clock. And finally, we have QA. For QA, QB is the clock, so that's my active edges. So for QA, assuming QA to be 0 to start with, that toggles on the first active edge, that happens here, and then toggles back again on the next active edge, which goes on, right? And the frequency of QA would be FC over 16. So you can use this circuit to create these signals of set duration, which you can use as timing signals. So you can actually use these particular circuit for generation of timing signals. For example, if I want a timing signal that's on for, let's say, 1, 2, 3, 4 clock cycles, I would use this particular signal, right? So I can actually use this to generate timing signals of set time durations. Not only that, you can also use this for frequency division. As you can see, with every subsequent stage, I am dividing the frequency by a factor of 2, right? So you can actually do this for frequency division as well. Oops. All right, let's see. Yeah, there you go. Wonder what happened there, but anyway. Any questions before we move on? And this particular circuit is also called a counter. This is called a counter, and we'll see why it's called a counter. Okay. Now, let's say if I monitor the clock signals, then the number of active clock edges, which are counted as clock signals. Okay. And if I monitor QA, QB, QC, and QD values, right, as a function of time. So on the 0th clock pulse, everything was 0. Everything was initial values were all zeros, right? On the first active edge of the clock, everything is still 0 except QD, right? My QD became 1. So except QD, everything was 0. On the second active edge, my QD became 0, my QC became 1, and then QB and QA are both 0 still. On the third active edge, so this is 1, 2, 3. On the third active edge, my QD became 1, my QC remained 1, right? On the third active edge, my QD became 1, my QC remained 1, my QB and QA are still zeros. On the fourth active edge, which is this one, my QD became 0, my QC became 0, dropped to 0, my QB became 1, QA remained 0. Okay. On the fifth active edge, that's the fifth edge, my QD became a 1, QC remained 0, QB remained 1, QA was still 0, and so on. So you can see the pattern, right? With every active edge, when I look at these together, the outputs together, I am essentially counting the number of clock pulses in binary. So that's the 0th clock pulse. That's the binary value of 1 happening at the first clock pulse, first triggering instance. Second triggering instance or second clock pulse, that's the binary value of 2, 3, 4, 5. In other words, this particular circuit is counting the number of clock pulses elapsed, right? So that's why this particular circuit is also called a binary counter. Okay, a binary counter. Okay, and one thing that we need to observe here, though, is my clock, the master clock, is only applied to the first flip-flop. For all the subsequent stages, the clock kind of ripples through these stages, right? The effect of the clock is seen through these outputs, which are applied as clocks to the subsequent stages. So in other words, these clock signals ripples through each stage, through these outputs, manifested through these outputs. And that's why this is also called what is called a ripple counter. This is a ripple counter. My clock is not directly applied to all the stages, but my clock is indirectly applied through these outputs. My clock influences, the master clock influences QD, right? And QD is applied as a clock to JC flip-flop, and so on and so forth. So the master clock, the effects of the master clock is kind of ripples through all of these stages. That's why it's called the ripple counter. Okay, so that's good. So it's a useful circuit. It can be used to generate timing diagrams. It can be used to count the number of clock pulses. And as a frequency divider. So it has multiple different uses for these kind of circuits. Having said that, let me ask you this. Do you see any issues with increasing the number of stages? Can we just add on, for example, this particular circuit with 4 stages, 4 JK flip-flops. this can give you a count from 0 to 15, right? So if I count down, so the last count would be 15, which is 1, 1, 1, 1. So it can count 16 values. 60 is a count. It has a total count of 16, and this is called a modulo. This is also called a modulo 16 counter. So with 4 JK flip-flops, I can obtain a 16 modulo 16 counter. If I add one more stage, right? If I add one more stage, then I would get a modulo 32 counter, right? Because now we have QA, QB, QC, QD, QE. So our count goes from 0, 0, 0, 0, 0 all the way down to 1, 1, 1, 1, 1. That's 0 to 31. So the total count is 32. So that's a modulo 32 counter. Okay. Likewise, if I want larger counts, all I have to do is just add one more stage. In this particular configuration, I can get a count by a factor of 2, increased by a factor of 2. Okay. All right. So in general, if I have n flip-flops configured this way, I would obtain what is called a modulo 2 to the n counter. So n flip-flops, a modulo 2 to the n counter. Oh, wait a minute. I should not have done that, but anyway. So n flip-flops or n JK flip-flops, I would get a modulo 2 to the n counter. In general, if I want to generalize it. Okay. Now, having said that, we cannot just indiscriminately add or keep on adding stages. Now, do you identify what could happen when I keep on adding the stages in this kind of a cascaded mechanism? Can anybody guess what can happen? You can chat, you can, or you can just unmute yourself and respond. Yeah, Tom. Maybe I'm not able to hear you what Tom is saying. Maybe you should just chat then, because somehow my speakers are not responding. So again, similar to what we saw for a n-bit adder, right? We would have similar problem here, as in, if I look at the timing diagram again, right? This is the master clock being applied. To the first flip-flop only. So in general, it's not a good practice to introduce logical elements in the path of the clock, just like what we have done here, because that can throw the circuit out of synchronization. Now, you will see that even though these circuits can respond fast, can switch very fast, there is still a non-zero timing delay. The timing delay, yes, exactly right. So non-zero timing delay, as in each, for my QD to switch, once this gets triggered, it will have its own timing delay, very small timing delay, but it's there. In other words, if I want to draw QD value, right, QD, so these are my triggering instances for QD. So instead of switching exactly at this point, it will have its own timing delay, right? So instead of switching exactly like this, here it will switch, it will toggle at this point, and instead of exactly toggling at this triggering instance, it will toggle with a timing delay, or let us say the average timing delay is TD. Okay. Again, TD is nanoseconds, it is a very small timing delay, but it is there. And likewise, for every triggering instance, you will basically have this slight timing delay. If it is just one stage, it really does not matter, it is imperceptible. Okay. Now, but remember that this particular signal is being applied as a clock to the next stage, So you can see that there is some finite timing delay, right, TD. On average, let us say the average time my flip-flop takes to get triggered, to change the output, to switch the output once it is triggered, is TD. Okay. Now, what happens to QC though? For QC, the timing delay with respect to the master clock gets added up, right. So, again, these are the triggering instances for QC. So, instead of my QC getting triggered here, this is where it should be. It should have actually got triggered. Now, it starts to get triggered with a timing delay of TD at this instance, right. Same thing here, and so on. So, you can see my timing delay for QC got added up. So, that is TD, that is TD plus another TD. So, the timing delay for QC was 2 times TD, right, 2 times TD now with respect to the master clock, 2 times TD. Now, this timing delay is now going to get propagated to the B flip-flop, JB and KB flip-flop. It adds its own timing delay. So, that the timing delay for this to respond with respect to the master clock is going to be 3 times TD, and for JA flip-flop that is going to be 4 times TD. So, in other words, if I keep adding stages, the timing delay associated with the last flip-flop is going to be n times TD, right, n times TD, assuming that you have n number of flip-flops there in this particular configuration. Now, my flip-flop would give me the right counter signals as long as my n times TD does not exceed the clock period, the clock period, right. As long as n times TD does not exceed that, I would still, even with the timing delays, I would still get the right sequences of pulses. Once it exceeds that period, then we have the desynchronization happening, right. So, we need to make sure that when we are designing a ripple counter, we need to make sure that you can only use so many stages, so that the combined timing delay is still less than the time period of the clock, okay. In which case we will get the right count and so on. Otherwise, you will get intermediate wrong counts in the counter. Okay. All right. So, again, a good practice in the digital design is you do not want to introduce anything in the path of the clock, because that can throw off the synchronization in the large scheme of things. So, ripple counter is useful especially for small counts, but then when we need larger counts, it is not a very useful circuit. Okay, so, it has its own limitations, and which needs to be addressed. Okay. And one way that we can address that is by designing what is called a synchronous counter. A synchronous counter, as in my clock is applied to each of the stage at the same time, as in each of my stages, each of my JK flip-flops are synchronized with the master clock. Okay, so, there is no delay in that sense. My clock does not have to ripple through these stages. Each of the flip-flop is applied with the master clock simultaneously. Okay. So, let us try to design a sequential synchronous counter, okay, synchronous counter. Just through intuition and just through intuition and some guesses, I guess. All right. So let's try to design a modulo 16 counter. That means I need to have 4 flip-flops, 4 JK flip-flops. Okay, that's the first thing. So let's draw them first. So let me draw my flip-flops. In this case, the first constraint is that my clock has to be applied to each of these stages simultaneously. So the same master clock is applied to each of these stages. Let me call this JD, KD, JC, KC, JB, KB, JA, KA, that's Q, QD, QC, QB, QA, okay, and then the first requirement is I want to make sure that each of these flip-flops are applied with the same clock. So that's the constraint I'm working with in this particular case. Okay. All right. Now the way we will design this step by step. Let's try to design this step by step. This is the desired sequence of counts, right? So that's the clock, number of clock pulses, QA, QB, QC, QD. This is the desired sequence of pulses or signals that I want to obtain. And to obtain that desired sequence, how should I configure this circuit for each of these flip-flop stages so that I can obtain that desired sequence, right? So let's say clock 0, I want everything to be 0, everything is cleared. On the first triggering instance, then I need to have QD to be 1, second 0, 0, I want this particular count, third will be 0, 0, 1, 1, fourth 0, 1, 0, 0, fifth 0, 1, 0, 1, sixth 0, 1, 1, 0, seventh 0, 1, 1, 1, eighth 1, 0, 0, 0, ninth 1, 0, 0, 1, and so on, all the way down to 15, where I want the count, the last count to be 1, 1, 1, 1, and then restart. Right? This is the desired sequence of counts that I need for each clock pulse. With each triggering instance, I want that particular count, these particular values on each of my flip-flops outputs. Okay. Now let's do it one step at a time. Let's try to get, with respect to the clock, let's try to get how do you get the QD values. Okay, let's start with that, and then we'll proceed to each of my QA, QB, and QC. Yes, that's exactly right. So we can just toggle, right? Because my QD toggles for each clock pulse, my QD toggles. So in this case, I can just simply say, okay, I will configure the first flip-flop, my JD and KD flip-flop, to be at 1. So that should work for QD. So we took care of QD. Now comes the question about QC. How do I get QC, the behavior of QC? I cannot touch the clock because the clock is already applied. So the only thing I can touch is JC and KC. What should be applied on JC and KC so that I can get this count, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, and so on. So it's off for 2 clock cycles, on for 2 clock cycles, off, on, and so on and so forth. What can we do? Any ideas here? How about applying QD directly to QC, to JC and KC? What will happen then? If I apply QD to be directly applied to JC and KC, something like that. When QD is 0, implies I'm applying a value of JC equal to KC to be 0, right? And for a flip-flop, when I apply JC and KC to be 0, that implies once it's triggered, the same value remains, right? That's called the memory state. Once the flip-flop is triggered, that means QT plus 1, the output is same as the previous output. That's the memory state. Okay? When QD becomes 1, as you can see here, when the QD becomes 1, implies I'm applying JC and KC to be a 1, right? That implies my QT plus 1, that means once the flip-flop is triggered, I am toggling the previous output, right? When the flip-flop is triggered. So that's the memory state. That's the memory. That's the toggle state. Now let's examine here. When QD is 0, my JC and KC values are zeros, right? My QC was 0 to start with. On the next triggering instance, my QC maintains the same value because my JC and KC were zeros. On the next triggering instance, that corresponds to a memory condition, so it retains the values. Okay? My QD itself got triggered, my QD itself got changed within that transition. Now QD became 1, right? That means my JC and KC values are applied a value of 1. Nothing happens right now because my flip-flop is not triggered yet. However, on the next triggering instance, which happens here, my QC gets toggled, right? Because my JC and KC values are 1, my QC gets toggled. At the same time, my 1 became 0 on QD. I'm applying a 0, 0 on my JC and KC. On the next triggering instance, that value, because I'm applying a 0, 0 on my JC and KC, that value is maintained. That value did not change, right? And in the meantime, at the same time, my QD becomes 1, right? My JC and KC becomes 1s. And on the next triggering instance, my QC toggles, right? And so on. So that way, when I apply QD directly to JC and KC, I am alternating between a memory state, memory condition, and a toggle condition with each clock cycle. Okay, so that way I'm able to maintain, a particular values for 2 clock cycles on JC and on QC. Okay. Any questions on this? Okay, with that said, how do I obtain QB? How do I obtain QB? So the hint is already there. We got QC, right, by toggling between memory and toggle states, right? The way QD toggles, the way QD is applied to JC and KC, we got QC. What about QB? Any ideas here for QB? Okay, AND gates, right? You can see for QB, I want this to be in the memory state for these many clock cycles. Okay, and then only when my QC and QD are both ones, I want to toggle QB. Right? I want to toggle QB. So in other words, if I apply QC and QD, this is QD and QC through an AND gate, and apply this as my inputs to both JB and KB, or JB and KB, then I should get that behavior, right? Because when both QC and QD are both 1s, I'm outputting a value of 1 here on JB and KB that configure this flip-flop as a toggle state, and on the next triggering instance, my value gets triggered, right? And this value is maintained until my QC and QD both becomes 1s again, which happens here, right? So 0, 0, 0, 1, 1, 0, I'm basically applying this value to be 0 on JB and KB. My value changes to 1 only when QC and QD both becomes 1, and on the next triggering instance, my QB again toggles. You see that? So that way I can get my QB value. So that's good. So QB I got QC, I got QB. What about QA? Any ideas for QA? Yes, DC, yes, perfect. So same thing here, right? If you observe QA, my QA should toggle when my QB, QC, and QD are all 1s. Until then, it should maintain the same value, right? So how do I make sure that happens? Well, I apply another AND gate between QB, QC, and QD. I already have an AND gate between QD and QC, so that QD, QC. I'll just apply another AND gate here and output that value to J and KA. And then that gives me my QA. So this is an example of how you can have a synchronous, this is also called a synchronous counter. The ripple counter can be also called as an asynchronous counter or asynchronous counter. This is a synchronous counter because my every stage is synchronized with the master clock. That's why it's called a synchronous counter. Okay, so the question is, what happens after 15, after the count of 15? After a count of 15, everything gets reset back to 0, 0, 0, 0, right? Because QD obviously goes to 0, right? QC, because this is 1, gets triggered, that's 0. Both are 1s, that means this gets toggled. All the 3 of these are 1s, that means this gets toggled. So it automatically goes to 0. So in other words, this particular counter, if you don't do anything, it goes from 0 to 1, 0 to 15, back to 0. So it keeps counting between 0 to 15, back to 0, 15, and so on and so forth. Okay, so it's an up counter. How do you make it a down counter? Where you're starting with 1, 1, 1, 1, I want to count down to 0, 0, 0, 0. Well, instead of monitoring QD prime, right? QC prime, QB prime, QA prime. Again, these are available, I'm just not showing them. So if you monitor those prime outputs, then you get a modular down counter. Okay? Questions? So we have modular up and modular down. And to Tom's question about can we have a explicit reset button or preset button by which we can actually force the output of a particular flip-flop to assume a particular value. Okay? And yes, absolutely you can have that. So for example, even though we don't show them, these particular flip-flops are designed to have, let's say J and K, Q and Q prime. These are also designed to have these preset and clear inputs. Okay, preset and clear inputs. Just like each of these circuits are active circuits, that means these have to be powered, right? Only then these can operate. So, and we don't show them actively every time, the power connection and so on. We assume them to be there. Just like that, we also have preset and clear inputs on my flip-flops, so that again the way I represented these inputs, right? Preset with a bubble, clear with a bubble. What they mean is these are called active low inputs. Active low inputs. What that means is, for this particular flip-flop, these inputs only work when I apply a low signal on preset or clear. So if I want to draw that, if I want to put that down in a table, right? Preset and clear inputs, the operation, then 0 obviously doesn't make sense. I cannot have both preset and clear to be zeros at the same time. Okay. 0 preset 0, clear 1 means that I am forcing Q to be a 1. I am forcing the value of Q to be a 1, assume a value of 1. Okay, because my preset and clear inputs are active low, applying a low value, low signal as in 0 signal on preset, 1 signal on clear, means that I am wanting to force my value of Q to be a 1. 1 0, that means I am forcing because this is again clear is an active low input, that means it's active when it's low. Clear is 0, that means I'm forcing the output of the flip-flop Q to be 0. Okay. And finally, you have 0, 1 1. In this case, this normal JK operation, normal flip-flop operation, right? Because those two inputs are not active anymore because I've applied a 1 and 1 values on both preset and clear. That way, this it basically my flip-flop basically resumes its normal operation. Okay, so that's about counters. Very important in the design of digital systems. You need to know how to design counters, how to apply counters, multiple different applications. All right. Any questions before we move on to the next topic? If not, let's now that we have gathered all the building blocks together, all the sequential building blocks. Now let's start looking at the application of these building blocks, right, in the design of what are called state machines. So let's start the new and final topic for this semester. Very important topic. I'm just going to get started here, and then we'll continue that after the break. Okay. So state machines. Okay. So what are state machines? As the name suggests, it's a machine that can exist in multiple states. Right? It's a machine that can exist in multiple states. Okay. A good example would be if you consider human beings themselves. We are state machines. We can be considered as state machines as well, right? And when we talk about human beings as state machines, can you think about what do you understand by state in the case of a human being? What does state mean? And I open that discussion for the whole class. What do you mean by state in the case of human being? See if you can chat, because it doesn't look like my speakers are working for whatever reason. Okay, alive versus not alive. Yes, that's a state. Condition. What can you elaborate on what do you mean by condition? I mean, emotion, okay, emotional states. Let's go with that. So, emotional states. So each individual is very complex. They go through these multiple different emotional states, right? And so let's do a quick exercise. Let's list out all the different emotional states that you can list for a human being. Emotional states that one can exist in, right? So at any given instance of time, we are in a particular emotional state, okay, happy state. Okay, let's start with something nice, happy. Let's see. Let's look at the chat. Let me monitor this. Okay. Condition, anger, happy, sad, anger. Okay. Now I do this exercise with each class. Every time I teach this class, this is a fun exercise. I do this just to see how many states you can come up with, how many unique states that you can come up with, and see if one class beats the other class. So let's see how many you guys can come up with. Anger, sad, sad, yeah, got sad. Anxious, okay. That's a state. Fear, I'll take that. Fear is a state, emotional state. Confusion, yes. That's 7 so far. Inspired. Okay, that's good. Love, yep, emotional state. Being in love, yes. Mind. Hungry, yes. That's a tricky one, but I'll probably keep it. Hungry, same as angry, maybe. Disgust, yes. Distressed. Relief, yep. Guilt. We had shame, right? Did we have shame? Did I not write that here? Okay, shame. 15, that's good. That's a good number already. Surprised. All right, I'll take that. Regret, yep. Annoyed. Annoyed is kind of similar to angry, but maybe a little different. 18th. Pride, okay. That's an emotional state. Compassion, yes. Melancholy, okay. Inspired, did we have inspired? I think we got inspired. Boredom, all right. Did I miss anything? Whimsy. Okay. So 22 emotional states you have identified, looks like. Calmness, I'll probably do that. feeling of calm, yes. Hope. Did we have hope before? Sad, anxious, love, hungry, disgust, distress, relief, guilt, shame. Okay, I'll take hope. That's a good one, actually. Satisfaction. Okay. Helplessness. Okay. You guys are good. So according to a CNN study that was published a few years back, they have identified 26 unique emotional states that a human being can exist in. 26 was the number. Excitement. Although students from multiple semesters, they did go beyond that. Excitement, right? Okay, excitement. So it's 27. Very good. You guys did a very good job. Okay. So I think you're very close, in fact, or better than the previous guys. So your class did very good in this aspect. So these are all the different states. So one thing that we have to understand is that at any given time, we are only in one of these states at a given time, right? We are not in multiple different states at the same time unless, I will not say unless, for most cases, commonly, we are only in one of these states at a given instance of time. And what takes us to transition to different states? What facilitates those transitions? Let me ask you this. So let's say I'm in a happy state. In this present instance, the facilitator of or what is the thing that facilitates the state transitions, as in going from one state to the other? Outside change, okay, so outside influences, so that's one influence. Outside influences. Acting upon me can facilitate that, or can be a determining factor of in what state I will be in the next instance, right? So I already gave you the internal dialogue. Yep, absolutely. Atmosphere. So all the influences. But the thing that facilitates those state transitions is time. So we have this feeling of time, the movement of time. We can feel it, right? And the time is the thing that facilitates us from one state to the next. Of course, the outside influences determine what states I'm going to be existing in. Outside or internal influences, internal talk, determines what states I'm going to be in. But then it's a time that takes us from one state to the next state. Okay, so that's something to keep in mind. So outside influences are the determining factors. These are the determining factors. Right? So you can think of these as the inputs to your system, and time is the facilitator to transition between multiple different states. Okay. Now, having said that, can you think of examples of machines now that can exist in multiple states? Of course, when we talk about machines, we don't have, we're not referring to emotional states anymore, right? Can you think of machines that can exist in multiple states, that can transition between states as a function of time and inputs? Of course, these are called state machines, right? And there are multiple of those available. A good example would be, for example, your washing machine. Your washing machine is a state machine. It can exist in multiple states. Right? You put the clothes in, you turn on the on button, and it automatically goes through multiple cycles. Right? You have the wash cycle, it rinse cycle, and you can consider each of those cycles to be a state for that particular machine. And it's going through each as a function of time. You are able to run that machine through multiple different states. Okay. All right. So since we are out of time, we'll stop here, and in the next 2 classes, we'll talk about state machines. Very important concept, very interesting concept, which pulls together everything that we have learned so far in the application of design of state machines. Okay. All right. We'll stop here, and then I'll see you guys next week. You guys have a very good Thanksgiving break, and would the dryer be a similar? Yep, absolutely. If it has multiple states, yes, a dryer could also be designed as a state machine. Thank you, guys.